Next, second law of thermodynamics. After the failure of the first law of thermodynamics, another law in the thermodynamics that was introduced is second law of thermodynamics. This second law of thermodynamics, it was introduced to explain the process in which enthalpy change is positive. For example, during the evaporation of the water, the enthalpy change is positive. Similarly, during the melting of the ice, the enthalpy change is positive. So, according to first law of thermodynamics, ice should not melt because during the melting of the ice, heat is being absorbed. Similarly, according to first law of thermodynamics, during the evaporation of the water should not evaporate because enthalpy change is positive. But evaporation of the water is continuously taking place and melting of the ice is also continuously taking place. Therefore, to explain the process in which enthalpy change is positive, another law called second law of thermodynamics was introduced. Next, in order to explain the spontaneity of the various endothermic process, the second law of thermodynamics, it has introduced one more thermodynamic function called entropy change. That entropy change is represented with the del S. Entropy change. This entropy change is represented with del S or ds. So, with the help of this entropy change, the second law of thermodynamics, it has tried to explain the spontaneity of the various processes. So, according to the second law of thermodynamics, in any change, if the entropy change is positive, that reaction or that change is spontaneous. That means, according to first law of thermodynamics, every change is spontaneous if enthalpy change is negative. But according to second law of thermodynamics, wherever if entropy change is positive, all those changes are spontaneous. That means second law of thermodynamics, it is trying to explain the spontaneity based on the entropy change, but not based on the enthalpy change. Therefore, according to second law of thermodynamics, if you closely observe, wherever if entropy change is positive, those changes are actually spontaneous. That means, say for example, if you observe the formation of the molecule from independent atoms. Here, when the two hydrogen atoms are independently present, if they combine with each other, if they get converted to hydrogen molecule, here actually the freedom of the independent hydrogen atoms is gradually decreasing. Therefore, when the freedom decreases, we can say the entropy of the hydrogen atoms is decreasing. So, according to the second law of thermodynamics, whenever if the entropy change is positive, that reaction is spontaneous. Here, the simplest meaning of the entropy change or entropy is disorderliness. Entropy is almost equivalent to disorderliness. This is disorderliness. So, therefore, according to second law of thermodynamics, wherever if entropy is positive, wherever if the disorderliness is positive, those reactions are spontaneous. Now, we observe this simple reaction. Here, when the two hydrogen atoms are in independent state, they will enjoy more freedom, they will exhibit more disorderliness. If they combine with each other, if they get converted into molecule, the degree of disorderliness will decrease or the degree of entropy will decrease. So, therefore, here if the entropy decreases, according to second law of thermodynamics, that particular reaction should not happen in the nature. Whereas, that should not happen in the nature. Whereas, whenever you observe the two hydrogen atoms, they always combine with each other, they always get converted into hydrogen. That means, according to second law of thermodynamics, even the formation of the molecules should not happen because during the formation of the molecules, the degree of disorderliness of the independent atoms are decreasing, hence the entropy is decreasing. Therefore, according to second law of thermodynamics, the formation of the H2 molecule should not happen. But formation of the H2 molecule takes place, formation of so many other molecules also takes place. Therefore, second law of thermodynamics cannot explain properly the formation of the various molecules. Next, before going into this, the other aspects of the second law of thermodynamics, let us discuss about the what is entropy, how to calculate the entropy during various changes. So, the simplest meaning of the entropy is disorderliness. Next, the entropy change can be represented with the del S or ds. Next, the absolute magnitude of the entropy cannot be determined. It is not practically not possible. Not only entropy, we cannot determine the absolute magnitude of any thermodynamic property, whether it is enthalpy change or internal energy change or free energy change or entropy change. the absolute magnitude of any thermodynamic property cannot be determined accurately. Only change in the any thermodynamic property can be determined. Change can be determined, del S or ds. Next term, this entropy change is a state variable. That means the magnitude of the change of the entropy do not depend on the path in which the process is carried out. It depends only on the initial and final states. Therefore, entropy is a state variable, like enthalpy change, like internal energy change. Since entropy change is a state variable, we can say the cyclic integral of the entropy change. Is 0. So, state variable is a normal language. In mathematical terminology, we can say the cyclic integral of the entropy change is 0. Next, the entropy. Next, when a process or any change, when it is taking place at constant temperature, the entropy change can be calculated based on the amount of the heat energy that is being exchanged with respect to temperature. Therefore, say at one particular temperature, at constant temperature, let us say this is the enthalpy change, or this is the heat energy change that is involved. This is the temperature at which that heat energy change is taking place. Therefore, if a change is taking place at particular constant temperature, just by taking the ratio of the heat exchanged with the surroundings with that of the temperature, we can calculate the entropy change. Next, see now if we use this formula, now we will get the units. Let us say enthalpy change in SI system. If we represent enthalpy change as joules per mole per Kelvin. Now we will get the units joules per mole per Kelvin. Next, see whenever if any thermodynamic property is expressed per mole, then automatically that entropy, thermodynamic property will become the intensive variable. So in this aspect, if we express the units as joules per mole per Kelvin, entropy change will become the intensive variable. Sometimes without the need of calculating the enthalpy change per mole, directly if we calculate the enthalpy change per given quantity of the substance, then in that case we will get the units joules per Kelvin. If we express the enthalpy change as joules per Kelvin, then under that condition enthalpy change will become the state variable. Here if you express the units as joules per mole per Kelvin, it becomes the intensive variable. Next, now let us observe the various changes that are taking place at a constant temperature. So one change that is taking place at constant temperature is a fusion. So during fusion, how to calculate the entropy change? The entropy change is the enthalpy change involved in the fusion with respect to temperature. Therefore, this temperature automatically becomes the melting temperature. This is one expression through which we can calculate the entropy change involved during the fusion. Fusion means during the conversion from solid state to liquid phase. At particular temperature, what is the enthalpy change involved in that process? By using that enthalpy change, we can calculate the entropy change. Next, during evaporation. During evaporation, how to calculate the entropy change? Entropy change is this is the formula that we use for calculation of the entropy change at during the evaporation at particular temperature. That evaporation taking place at particular temperature is nothing but the boiling point. Therefore, this is the boiling point of the liquid. This is the enthalpy of evaporation involved in the process. Next, here when instead of calculation of the entropy change at given temperature, if you want to calculate the entropy change over a given range of the temperature, then we have to integrate this expression. Therefore, entropy change during range of temperature. During one particular range of the temperature, how to calculate the entropy change? ds. Say for example, let us say this is the enthalpy change involved in that particular range of the temperature. Particular range of the temperature. So already in the thermodynamics we have one expression for the enthalpy change. That expression is NCP dt by T. If you want the entropy change over a particular range of the temperature, now integrate this expression over that given range of the temperature. T1 and T2. But here T1 and T2 should be two temperatures within the single phase of the substance. For example, if the particular substance is in the liquid state, this temperature T1 and T2 represent the temperature of liquid at lower temperature of the liquid at a higher temperature. T1 and T2. Here T1 and T2 belongs to two temperatures. Two temperatures of liquid or solid. Liquid or solid. Next, say during the if you want to calculate the entropy change during the phase change as well as between the two different phases. During change of phase as well as during change of temperature over a given phase. So for example, we want to calculate the entropy change. We want to calculate del S from solid state to liquid state. Solid state to liquid state. Therefore, the total number of stages involved in the conversion from solid state to liquid state is, this is a solid to liquid. At one particular temperature, equilibrium will be established. That temperature is called the temperature of the fusion. So first we have to calculate the entropy change at the fusion. That means at particular freezing point. Then within the liquid state, from one temperature to another temperature, T1 to T2. Del S is equal to entropy del S of solid, del S of the solid at freezing point, plus del S of liquid, del S of the liquid, del S of the solid at freezing point, this one, del H fusion by temperature, plus del S of the liquid within the given range of temperature, that is NCP ln T2 by T1. Next, how to calculate the entropy change of the ideal gases. The entropy change for the ideal gases can be calculated by using the expressions proposed by the first law of thermodynamics. This is first law of thermodynamics. By using the first law of thermodynamics, we want to calculate the entropy change. So if you use the first law of thermodynamics, the entropy change is dq. That means the heat that is exchanged reversibly, with respect to temperature. With respect to the temperature. That is entropy change according to the first law of thermodynamics. Next, according to first law of thermodynamics, the expression is this one. u p dv dq. Therefore, del s is equal to dou q reversible. This is a reversible by t. Therefore, du plus p dv upon t. Therefore, the next step is du upon t plus p dv upon t. For ideal gases, we can replace this p with the nRT by v, because we have PV is equal to nRT. Therefore, P is equal to nRT by V. Therefore, the next step is du by T plus nRT by V into T. This is in place of P, I am substituting nRT by V. Next here nRT by V. Next here dV and T are there. Next this T and this T, you cancel it. So, therefore, du by T plus nR dV by V. dV by V. Next in the same thermodynamics, we have one relation between the internal energy and the CV. Here this is a du is equal to NCV dt. Therefore, I am replacing this du with the NCV dt by T plus nR dV by V. dV by V. Now, over a given range of the temperature, we want to calculate the entropy change. Over given range of temperature, we want to calculate the entropy change. Therefore, del S is equal to NCV dt upon T. Integrate this term between T1 and T2 plus nR dV by V. Integrate between V1 and V2. Therefore, the next step is NCV. This is a ln T2 by T1. This is a nR ln V2 by V1. Therefore, the del S change in entropy for an ideal gas is NCV ln T2 by T1 plus nR ln V2 by V1. This is the expression that you can use to calculate the total entropy change by considering the temperature change as well as the volume change. That means, wherever in any numerical problem, if they just ask the entropy change of the ideal gas, in that problem, if two different temperatures and if two different volumes are given, always use this expression. Next, say for example, if temperature is maintained constant, if temperature is maintained constant, then del T is equal to 0. Therefore, the first term will become 0. Therefore, NCV ln T2 by T1 is equal to 0. Therefore, del S is nR ln V2 by V1. So, this is the formula that is used to calculate the entropy change when temperature is maintained constant. If temperature is maintained constant, the process is called isothermal process. Therefore, in any numerical problem, if they ask you to calculate the entropy change at constant temperature or in isothermal process, use this formula for calculation of the entropy change. Next, say for example, instead of maintaining temperature as constant, if volume is maintained constant, then how to calculate the entropy change? Say volume is maintained constant means V1 is equal to V2. Therefore, the second term will become 0 or disappears from the expression. Therefore, final expression becomes del S is equal to NCV ln T2 by T1. Therefore, now I will represent that expression. Therefore, if volume is kept constant. Volume is kept constant, then dV is equal to 0 or V1 is equal to V2. Therefore, del S is equal to NCV ln T2 by T1 plus NR ln V1 by V2 by V2 by V2, or this expression becomes 0. Therefore, NCV ln T2 by T1. This is the expression that is used to calculate the entropy change when when the volume is kept constant. Next, how to calculate the entropy change if pressure is being maintained constant. Now, you see we have this relation P1 V1 upon T1 is equal to P2 V2 upon T2. Therefore, V2 by V1 is equal to P1 T2 by T1 P2. Therefore, this del S is equal to NCV ln T2 by T1 plus, in place of V2 by V1 NR, in place of V2 by V1 I am substituting this one, NR P1 T2 by T1 P2. Therefore, I will represent this expression like this: NCV ln T2 upon T1 plus NR NR ln T2 by T1 plus NR ln P1 by P2. Next, I am merging this portion and this portion. Therefore, I will write like this: NCV plus R ln T2 by T1 plus NR ln P1 by P2. This is CV plus R, we know that is a CP. Therefore, NCP ln T2 by T1 plus NR ln P1 by P2. Therefore, in any numerical problem, if pressure change or pressure factor is involved, use this expression for calculation of the total entropy change. Use this expression. Similarly, if pressure is maintained constant, this term will disappear, then entropy change is equal to ds into NCP ln T2 by T1. Therefore, that expression I will show you. If pressure is kept constant, dP is equal to 0. Therefore, del S is equal to NCP ln T2 by T1. Similarly, if temperature is kept constant, del T is equal to 0. Therefore, del S is equal to this one, NR ln P1 by P2. This is the another expression. Therefore, based on the data given in the problem, by using one of these expressions, you can solve all the numericals related to entropy change involved in the ideal gases. Calculation of entropy change during isothermal reversible expansion of the ideal gas. Calculation of entropy change during isothermal reversible expansion of ideal gas. That means when temperature is constant, that means when dt is equal to 0, change in internal energy is also 0. Change in internal energy is 0. Therefore, according to first law of thermodynamics, it is dou q is equal to du plus minus w, or dou q is equal to du plus p dv. Therefore, according to first law of thermodynamics, dou q is equal to minus w, that is equal to p dv. Therefore, entropy change del S is equal to dou q by T. That is equal to minus w by T. That is equal to minus. For w already we have derived the expression, that is w. Therefore, w is equal to minus nRT ln V2 by V1 whole divided by T. This T and this T will get cancelled. Next, now this minus becomes plus. Minus plus nR ln V2 by V1. See, the same expression we have already derived in the earlier topic. See, the similar expression we got, because in the earlier topic we have discussed one point, calculation of the entropy change during the isothermal process, or when temperature is kept constant. Here also, when the gas is undergoing reversible expansion under isothermal conditions, we will get the similar expression, that is plus nR ln V2 by V1. Next, you observe the final expression of the entropy change. In the final expression, we have one term called N. N means quantity of the gas. So therefore, if any thermodynamic property depends on the quantity of the gas, then that is extensive property. Next, here R, this is universal gas constant. We know universal gas constant is constant for all gases, and moreover this universal gas constant is intensive variable. Next, this is initial volume and this is final volume. Therefore, initial volume and final volume. Therefore, the total entropy change depends only on the initial and final volume of the given gas. That means entropy change do not depend on the path through which the gas undergoes expansion. Since the entropy change do not depend on the path, therefore entropy change can be called as the state variable. It does not depend on the path. It is not a path variable. It is only a state variable. Since it depends on the quantity, it can be called as the extensive property. Next, calculation of the entropy change during the reversible compression of ideal gas. Calculation of entropy change during isothermal reversible. Calculation of entropy change during isothermal reversible compression. Reversible isothermal compression of ideal gas. So again, here again we are calculating the entropy change based on the first law of thermodynamics. According to first law of thermodynamics, dt is equal to 0, therefore du is equal to 0, therefore dq is equal to minus w, that is equal to p dv. Therefore entropy change is equal to d dou q by t, that is equal to minus w by t. Next, during the isothermal reversible compression, already we have derived the expression for w. Derived the expression for w, that is w is equal to here minus nRT ln V1 by V2. Here again Tt will get cancelled. Next, this is minus into minus plus nR ln V1 by V2. Or else I will represent this as minus nR ln, I will bring V2 to the numerator, ln V2 by V1. That means during the compression, gas molecules are coming closer and closer together. If the gas molecules come closer together, the degree of freedom of the individual molecules decreases. When the freedom decreases, the entropy also decreases. That's why that decrease of entropy we are showing with this negative sign, minus nr ln V2 by V1. Next, the total entropy change involved in the expansion as well as in compression. Total entropy change involved in expansion and compression. Total entropy change involved in expansion and compression of ideal gas. So del S total is equal to del S involved in expansion plus del S involved in compression. Del S involved in compression. Therefore, during expansion we got this expression nr ln V2 by V1. During compression we got this expression minus nr ln V2 by V1. See the magnitude of the V1 and V2 in this expression, magnitude of V1 and V2 in the second expression, both are same. Therefore, when the magnitudes are same, if this is a plus x, this is minus x. Therefore, the resultant of these two terms is 0. Next, whenever if the total entropy change is calculated during any process, if we get the 0, that implies that total entropy change is what is called net entropy change is 0. Therefore, that is called a state variable. Since total entropy change, since the total entropy change is 0 during expansion and compression, therefore the process is called a perfect cyclic process, or the entropy change is a state variable. Since the total entropy change is 0, therefore it is a state variable. It is state variable. Or else say for example, if you integrate any thermodynamic property between similar limits, if the sum becomes 0, then the cyclic integral of that thermodynamic property becomes 0. Whenever if the cyclic integral of any thermodynamic property becomes 0, then that is called state variable. So here, therefore, del S here between V1 to V2 and V1 to V2 plus V2 to V1 is equal to 0. Calculation of entropy change during isothermal irreversible expansion of ideal gas. So again we are calculating according to first law of thermodynamics. We have dou Q is equal to du plus pdv. Here at isothermal conditions, du is equal to 0. If dt is equal to 0, du is equal to 0. Therefore, dou Q is equal to pdv or minus w. Therefore, entropy change is equal to dou Q by T or minus W by T. This work already we have calculated in the earlier topic, that is minus, in place of W this is P external V2 minus V1. Next, calculation of the entropy change involved during the isothermal irreversible compression of the gas. Calculation of entropy change during isothermal irreversible compression. Isothermal irreversible compression of ideal gas. Here again, according to first law of thermodynamics, we are calculating. We have dou Q is equal to du plus P dV. If temperature is constant, change in internal energy is constant. Therefore, dou Q is equal to P dV, that is equal to minus W. Therefore, entropy change is equal to minus W by T. Next, for work we have derived the expression already in the earlier topic. Therefore, minus here P external V1 minus V2 by T. V1 minus V2 by T. Therefore, the total entropy change involved during the expansion as well as the compression. Therefore, del S total is equal to del S expansion plus del S compression. During the expansion, the entropy change is, here we have calculated earlier, that is minus P external V2 minus V1 by T. V2 minus T. Next, plus P external V1 minus V2 by T. V1 minus V2 by T. Next, this I will represent as P external V2 minus V1 by T. This I will represent it as P external V2 minus V1 by T. V1 by T. Next, during the expansion, the gas has to do work against the external pressure. During compression, the surroundings have to do work against the pressure of the gas. Therefore, during compression, the external pressure, the magnitude of the external pressure is more. During compression, the magnitude of external pressure is more. Magnitude of the external pressure is more. Therefore, the total magnitude of this term will increase. Magnitude of external pressure is more. Therefore, the sum of above terms become positive. Sum of the above terms become positive. Therefore, the del S total is positive. Based on the above statement, I will give one simple numerical example. Based on that numerical example, easily you can understand why the del S has become positive. Say for example, this is the system. Now let us say the system here, gas is undergoing expansion irreversibly in a single step. So for irreversible expansion to take place, or if the irreversible temperature transfer to take place, say for example, the temperature of the system is 300 Kelvin. Let us say the temperature of the surroundings is 500 Kelvin. So when such a large difference of temperature is existing between system and surroundings, at a time large amount of the heat will be transferred. Let us say the amount of the heat transferred here is let us say some 100 kilojoules per mole. 100 kilojoules per mole. Therefore, now we want to calculate the total entropy change involved in this transfer of the heat. The total entropy change is entropy of the system plus entropy of the surroundings. Entropy of the system is heat gained by the system upon 300. Next, entropy of the surroundings, heat lost by the surroundings upon 500. Now, if you take the sum of these two terms, say this is 100 by 300, this is 100 by 500. So, if we take the sum of these two values, we will get the positive. Therefore, here here because of this more magnitude for the denominator term, this it will become less, then finally the result will become the positive. That means whenever if the process is irreversible, the sum of the entropy changes of the system and surroundings always becomes positive, or the entropy change of the expansion plus compression always becomes positive. Next, the entropy change involved during the free expansion. Entropy change involved during free expansion. Free expansion. Next, during the free expansion, the temperature of the gas will remain constant. During free expansion, the temperature of gas will remain constant. They remain constant. Therefore, del S of gas can be calculated by using the following expression. It is del S of gas is equal to nR ln V2 by V1. nR ln V2 by V1. Next, here surroundings are neither losing the heat energy nor gaining the heat energy. Therefore, the entropy of the surroundings will remain constant. Surroundings are neither gaining heat energy nor losing their energy. Therefore, the entropy of the surroundings will remain same. Therefore, entropy of surroundings will remain same. Therefore, now del S total is del S system plus del S surroundings. Del S system is nR ln V2 by V1. Surroundings is 0. Therefore, nR ln V2 by V1. That means this term is positive. Therefore, the total entropy change is positive.